Hello, everyone. Thank you for having me. My name is Thomas Gaudin. I am a second-year master's student at New Mexico Tech. I study under Dr. Ryan Norris. Today, I'm going to be talking about my master's thesis research investigating mass transfer in symbiotic stars. So let's start by defining exactly what a symbiotic star is. Symbiotic stars are a rare type of interacting binary system. In fact, we only know of about 290 symbiotic stars that exist within the Milky Way. Now, these systems are defined by three main components. The first and most important component for this study is the cool giant. This is orbited by a hot compact object. This is typically a white dwarf, but in the past has been observed to be a neutron star or even a hotter main sequence star as well. The third component, and the most interesting for mass transfer in these systems, is the dense circumstellar medium, the cloud of gas and dust that surrounds both stars. This is the best evidence that we have that these systems are experiencing active mass transfer, that the red giant is losing mass to the white dwarf. Now, symbiotic stars are unique in that they are the widest type of interacting binary. Is relative to most interacting binaries, these periods of hundreds of days and orbital separations of approximately 1 astronomical unit are extremely wide to be an interacting system. We think that symbiotic stars are connected to several important late-stage stellar objects. Some examples of these would be planetary nebulae, soft and hard X-ray sources, cataclysmic variable stars. We also have evidence that the symbiotic stars are a possible progenitor system for type 1a supernovae. However, these connections are not very well defined and all hinge on this concept of mass transfer. So, mass transfer in symbiotic stars is a very active area of research in the systems. The big question is what mechanism drives mass transfer from the red giant to the white dwarf. We know that the giant loses mass to the dwarf. The question is, how is this done? This question revolves around the shape of the giant. If we see our giant filling its Roche lobe looking in this nice teardrop shape, then we say that the star is experiencing Roche lobe overflow. It exchanges mass just like most interacting binaries do. However, it's possible that we don't see that teardrop shape when we look at these giants. Instead, we see a much smaller, more circular star that is underfilling its Roche lobe. If we see the star underfilling its Roche lobe, then we know it's not experiencing Roche lobe overflow, that instead we're going to see the giant experience mass loss through a mechanism that is dominated by the stellar wind of that giant. If we can constrain exactly which mechanism is dominating the mass transfer process in these systems, then we can start to inform our models of how they're going to evolve over time, start to connect them to other important late-stage stellar systems. We'll even be able to calculate things such as the expected stable lifetime of symbiotic stars and the expected rate of mass loss from the giant. In the past, authors have primarily investigated this topic using photometric methods. They searched for ellipsoidal variations in the light curve of the giant in order to try and learn about the geometry of the system. This ellipsoidal variation was thought for many years to be significant evidence in favor of Roche lobe overflow in the systems, that giant was filling the Roche lobe. In recent years, however, there has been some doubt cast on that analysis. There's thought that maybe the stellar wind of the giant could be filling that Roche lobe instead of the photosphere of the star, and that would mimic those ellipsoidal variations. This is why in the 2010s, authors turned to optical interferometry to start investigating this topic. This was investigated twice using VLTI during the 2010s. The most famous observations were done by blind using VLTI to observe the target system SS-LEP, which we see over here. Work was picked up by Boffin in 2014, observing 6 more systems. As we can see from blind's observation, there's not very much evidence of that teardrop-shaped structure in the star. Instead, we see a star that's slightly asymmetrical, but clearly underfilling its Roche lobe. Boffin's study found 2 targets were filling its Roche lobe, but an additional 4 were underfilling that Roche lobe. So their results have so far been inconclusive, and open questions were left from both studies about the geometry of each system. The only way that we can turn to answer these questions is to go to a telescope with a much higher resolution. We need to be able to resolve the surface clearly of each giant in the symbiotic star system to check for that asymmetry, to check for the presence of a teardrop shape. This is why we are using the char array for this study, so that we can resolve features as small as 0.5 milli-arcsecond on the disk of giants, resolving the surface of most symbiotic giants within about a kiloparsec of Earth. Now for this study, we observed 4 symbiotic stars that were nearby. Our targets were V1472 Aquila, EG and BD Cam, and SU Lin. The observation dates for this study were in the fall 2021 semester. We have one epoch observed for each target. We got a couple of brackets across multiple nights on each of our targets. We were using MERC-X on Chara in order to gain maximum resolution, both in UV space for imaging and for maximum resolution to resolve the surface features of these giants. Our analysis is a combination of both model fitting and image reconstruction techniques. On the model fitting side of things, we used the program OI tools to fit 3 different geometric models created within the software to our observed visibility data. We can see over here for target SU Lin, our red corresponds to the model that we created. Black would be the observed data from the system. Below are the residuals from the fit. Our goal was to minimize the chi-squared from each of these from the models to determine which model best describes the geometry of the system. For this project, we followed the results of Boffin, or the methodology of Boffin, and created a model of a uniform disk, a model of an elongated disk that was more oval shaped, and then a third model of our own design that was a hybrid small uniform disk overlapped with a larger elongated disk. We expect that the uniform disk would fit best to a star that's underfilling its Roche lobe is very circular. The elongated disk was chosen to mimic that teardrop shape of a Roche lobe overflow star. And then the hybrid elongated disk model was created to sort of fill the in-between space, a star that has asymmetric surface features, but might not be filling the Roche lobe completely. On the imaging side of things, our image reconstruction was performed using squeeze. Reconstruction was completed both with and without a prior of a uniform disk. We chose both of these algorithms and compared the results in order to make sure that there weren't any artifacts present in our image reconstruction that we're seeing with the prior or with no prior when we did the reconstructions. We also averaged 10 chains of this reconstruction process in order to smooth out variations that were created through this process. Following the processes of Norris 2021, we used 3 regularizers: total variation, L0, and Laplacian regularization were chosen. We varied the hyperparameters for each target in order to minimize the reduced chi-squared of our fit to data. In addition to performing image reconstructions, we additionally simulated observations of these reconstructed images and fit that data back to both our closure phase data and our visibility data for each target. This just once again provides another sanity check that the asymmetrical structures we're seeing in the disk, the geometry that we're seeing from our images, are comparable to those that we're seeing from the observed data. Onto our results. For our model fitting phase, we fit each of our 3 models to our 4 targets, and we found interesting evidence of asymmetry, but very little evidence of a Roche lobe from our model fitting. So we see for V1472 Aquila, BD Cam, and SU Lin that we were able to improve our chi-squared from our model fitting by almost a factor of 2 in each case by fitting the hybrid model in favor of either the elongated disk or the uniform disk model. This shows us there are asymmetrical behavior going on in each of these 3 disks, but there is not much evidence that these stars are Roche lobe filling. It seems like each one is underfilling its Roche lobe just from looking at these model fits, especially although we do see that evidence of asymmetrical behavior. The 4th target, e.g. and, is by far our smallest target, and it's fit almost equally well to each of our 3 models. This sort of led to inconclusive evidence in favor of any model, or in favor of any asymmetrical structure in this target. This one might just be too small for us to resolve the surface features on the star. And now we present the results of our imaging. These are the highest resolutions ever taken of symbiotic stars. Now we see once again that the images back up the results that we're getting from our model fitting data. We see in target SU Lin, B1472 Aquila, and BD Cam that the stars are clearly not spherical. We are seeing evidence of distortions along the surface of the disk. We are also seeing very unique surface features that are present in each of these 3 stars. And we think that this is likely not due to Roche lobe filling. Instead, 2 of these stars, SU Lin and BD Cam, are both AGB stars. We think that these are likely due to thermal convective cells on the surface of each of our targets. B1472 Aquila is a little bit less evolved. It is only a red giant, but it is also showing these surface features as well that would be sort of more characteristic of thermal convection than of a star that's filling its Roche lobe. We're still not sure exactly what some of these surface features are, especially the sort of bipolar lobe structure that we see on V1472 Aquila, although that is something for us to observe and sort of study more in the future. As we look to EG and we see again that it backs up the results of our model fitting. This is a very small star. We aren't quite seeing enough resolution to be able to tell if there are these same sort of small distortions around the edges of the disk. Although we do see a very interesting small dark area that sort of dominates the surface of the star. This is once again another surface feature that we'd like to analyze as we move forward with this project. In conclusion, these are sort of still the preliminary results. They're very promising preliminary results, especially as we start to see evidence that there's not, or see very little evidence for Roche lobe at this orbital epoch. From our observations and analysis, it's unlikely that Roche lobe overflow is the dominant mass transfer mechanism that we're seeing in these 4 symbiotic stars. Instead, it seems that these 4 systems are dominated by wind-driven mechanisms instead of a Roche lobe overflow filling mechanism. However, we can't quite constrain the role of the giant's wind yet in this mass transfer process. We are still only observing using Merck-X in the H band. We would like to observe these targets using both Spica and Mystic to get data in both visible bands and the K band as well, to see if maybe there is a wavelength dependence or a temperature dependence for these asymmetrical structures. We believe that this would be able to tell us more about the role of the wind than these simple observations in the using Merck-X in H band. We also see that these results clearly motivate a need for future study. We are only seeing each star at one point in the orbit, so we can't conclusively rule out that Roche lobe overflow is a part of what we're seeing in these systems. Instead, the only way we can actually rule this out is through a long-term monitoring process. We need to observe the stars at multiple configurations to make sure that we are not just seeing an artifact of the position of the white dwarf hiding the Roche lobe from us. It could be behind the star or not visible for some other reason due to the positioning of the white dwarf. So we need to observe these stars multiple times over the next couple of years so that we can start to sort of rule out that Roche lobe being present in any orbital configuration for the system. We're also only seeing a sample size of 4 targets. V1472 Aquila does overlap with the targets observed by Boffin in 2014. So there are only 10 symbiotic stars that have ever been observed using interferometry. That's not enough for us to draw general conclusions about what this means for the entire populations of galactic symbiotic stars. We need to observe more targets over the next few semesters to start to draw more general conclusions. This work is going to continue beyond just my master's thesis project. This is just the beginning of this project. We do hope to make significant progress on observing more targets and monitoring these systems over time over the next couple of years. We also hope to observe these systems in multiple wavelength bands to start to constrain the temperature dependence of the wind in each system. With that, I would like to thank my advisor, Dr. Ryan Norris, for being so helpful in this master's thesis project. This has been an excellent way to spend a couple of years. I've been very excited about doing this research. It's been a great project for me. So, and with that, I would like to take any questions that anyone may have.
Okay, do we have any questions? Okay, it looks like we have a question in the chat window. It says, Julian says, you've talked about regularization for your fit, like total variation. What method did you use to estimate the best hyperparameter value?
So for this particular project, we just sort of used sort of a random walk to try and figure out which one what would best minimize the chi-squared. I believe Ryan has some more systematic methods that he's used in the past to sort of constrain what the best regularization hyperparameter is.
Okay, and we have a question from John in the audience.
Yeah, go for it.
John Young, just a comment on the images that you showed. There seemed to be a lot of bright spots preferentially around the limbs of the stars. And that seems sort of physically unlikely to be convective features because you're not seeing to, you're only seeing to very shallow depth around the limbs. So it seems more likely that they're image reconstruction artifacts.
Yep.
Okay, and I'll ask one quick question. Any chance that you could detect some of the companions in these systems?
The companions are probably outside of our field of view. They are, like I said, separated by hundreds of solar radii from the star. Also, they are white dwarfs, so they're not likely to show up, especially in Merc-X in the near infrared. There is a chance that we might be able to detect an accretion disk if it was found around one of these white dwarfs, although we have not sort of found one yet that would be likely to be visible.
Okay, let's thank our speaker again.